Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show a very important CFD aerodynamic analysis. It will be a aerodynamic analysis, together with that it will be CFD parametric study and optimization of a Lamborghini car. You can see the model. This is not the actual model. This is a miniature of the car. While modeling this one, we have kept the length of this one is approximately 1 meter, as this is a miniature, and width of this one we kept approximately 1/3 of that. This is a very important analysis, and this analysis is not like the previous ones. It is little bit different. We will be showing parametric study and optimization. Actually, while purchasing any kind of car, we need to see a lot of other parameters like what will be the drag force, what is the full force, etc. We'll see the importance of all this drag force and this full force behind this analysis. As an example, suppose we want to purchase a car, and we can see that some specific velocity is provided for that. We cannot run the car with more than that velocity, that is optimum velocity. In this model, the optimum speed or maximum speed of that car will be actually 54.96 meter per second. That is also very high. Now I'll show in our analysis why the velocity of this model should not be more than 55 meter per second. Though 55 meter per second is very high enough, our task will be to show the maximum velocity of this car. If the velocity of this car is more than 55 meter per second, in that case, it will not have that much of control over the car and it cannot apply brakes in this condition. Let's understand this one by one through this analysis, right? Okay. Now, before starting this analysis, we should understand that this drag force and full force is very important in this case, because drag force is the force which is opposing the velocity of the car. If drag force is more, in that case velocity of the car will be less. Similarly, full force is the force experienced by that vehicle or car from downward direction. It will try to move the car in the upward direction. If the full force is less than the weight of the car, it will be better one. We mean that if full force is more, in that case the car wheels will not have that much of contact with the ground. At high velocities only, full force will increase, and in that case the car will have less contact with the ground. So in that case we cannot apply any brake because frictional force will be less in that case, right? So with this analysis we'll show how the velocity of the car is maximum 55 meter per second, right? Here in this case we are not going to set up the simulation parameters and other things. We'll start directly from the simulation. What we have done in this case, for initiating the flow simulation environment, we need to start the simulation from wizard here, and next to that we need to select some other parameters. We have already run this simulation, so we can go a little bit back and see what we have done. From these general settings, it was an external analysis, and we considered fluid flow conditions, and gravity we have considered. In this case, gravity direction was actually y, right? Another very important condition is actually initial ambient conditions. In this case, temperature is not very important, and pressure is actually 101.325 Pascal. This is normal atmospheric pressure, and temperature it is actually 20.5 degrees centigrade. That is 293.2 Kelvin. This temperature is not that much of important in this case, so we are not bothering about this one. But very important factor is actually velocity of the car, right? From this one you can see that car will be moving in the z direction and air will be moving opposite to that one. So in this analysis we are considering the velocity of the car will be 40 meter per second. It will be moving along z direction. That's why the velocity of air will be minus 40 meter per second along z. We have kept that one here itself. Velocity of the car is minus 40 meter per second at z direction, because car will be moving along z with a speed of 40 meter per second, right? So these are the initial conditions. With these initial conditions we have started the simulation, right? These are the only boundary conditions we have kept. In our analysis we have decided several global goals and also some surface goals. The global goal was actually average total pressure, average velocity, drag force and frictional force. Drag force, frictional force and lift force, all these are actually global goals. Excluding that one, we also decided some kind of surface goals, and here in this case we have determined separate surface goals at specific locations. That means we have selected average total pressure on wheels on the front surface of this car, on the top surface, and also average total pressure on the side walls. So these are the different goals we have determined, and we have already run this one, so we can check the results from here. As I told before, this is not like previous analysis. We are not bothered about different cut plots of pressure, temperature, velocity, etc., because all these things we have already seen in similar type of analysis. In our analysis, we'll see why the velocity of the car is maximum 54.96 meter per second, right? Okay. Now another thing I want to say that while determining the coefficient of drag of this vehicle, we need to find out the projected frontal surface area of that car. Let us see how we determined this coefficient of drag. For that, we need to go back to the model. This is the model, and you can see at the back side at a specific location we have created some kind of space. Some sketch is created there backside, and on that specific space, if you see from front side, no, it will be exactly the projected frontal area of this car, right? On this specific sketch, we have provided some kind of areas by extruding this surface, and from this evaluate tab found the area of this specific frontal surface, right? Now while finding the coefficient of drag, that is equal to twice of drag force divided by density of air multiplied by velocity of that car into frontal surface area. Frontal surface area in this case equal to 0.0524 meter square. As this is the miniature of the Lamborghini car, so we are not having the actual surface area or actual dimensions. So this is little bit of smaller compared to the actual model, right? So this is the expression of this coefficient of drag, and we have selected absolute value of that one, in which this should not be negative, definitely, right? And this one is unitless. Okay, let us close this one. In first analysis, we are considering that velocity of the car as 40 meter per second. Based on that velocity, we'll see different parameters like drag force, friction force, lift force, and different pressure at different surfaces. In our case, pressure at different surfaces are not important. Our important is actually lift force, drag force, and also frictional force. As we have run this one, so let us see the goals. The goals can be seen from here itself, from results. Now directly we will go back to the goal plots, right? Insert goal plots, and we can see results from here, or we can export it to Excel. Let us see all these results from here itself, right? So show, these are the results you can see, and you can see all these results in the form of graph, also from summary. Let us convert it to history, right? First one is global goal. It is average total pressure on this Lamborghini car. Second one is average velocity. You can see average velocity, here it is, after 78 numbers of iterations. Average velocity is actually 38.86 meter per second. Next one is drag force. You can see after 78 numbers of iterations, drag force is actually 28.71 Newton. It is negative because it is in the opposite direction of cars. Next one is actually frictional force. Again, you can see here after 78 numbers of iterations, friction force is actually 0.94 Newton, and after 78 numbers of iterations, lift force is actually 5.54 Newton, right? As I told before, our task will be to see the maximum velocity of this vehicle. So in that case, lift force is very important. At the same time, this drag force is also important, right? Okay. So these are the values we got from normal aerodynamic analysis of this Lamborghini car. Next to that, what we'll do, we'll perform one parametric study. Let us close this one, right? Okay, fine. We know that as the velocity of the car increases, the parameters like lift force and drag force also increases. Now, how does it increase? That one will show through this parametric study. In this parametric study, we'll change the different velocities, and we'll see at different velocities what will be the different goals like frictional force, drag force, lift force, etc. Right? Now, let us see the study. This is design of experiments and optimization. Let us see what it is. In this design of study and optimization, what we've done is we have selected the velocity of the cars from 10 meter per second to 70 meter per second, right? And within these values, what will be the different values of this lift force and drag force, etc.? We can check it from here, right? Let us see the scenarios. We have run this one for 7 numbers of iterations. You can see when the velocity of the car is 10 meter per second, in that case, you can see lift force is 0.386 Newton and drag force is 1.79 Newton. In the second experiment, you can see that when the velocity of the car is 20 meter per second, in that case, drag force is 7.17 Newton and lift force is 1.412 Newton. Third experiment, when the velocity of the Lamborghini car is 30 meter per second, in that case, drag force is 16.11 Newton and lift force is 3.06 Newton. In the fourth experiment, when the velocity of the car is 40 meter per second, in that case, drag force is 28.6 Newton and lift force is 5.29 Newton. In the fifth experiment, when velocity of the car is 50 meter per second, in that case, drag force is 44.95 Newton and lift force is 8.311 Newton. In the sixth experiment, when the velocity of the car in z direction is 60 meter per second, in that case, drag force is 64.78 Newton and lift force is 12.01 Newton. And finally, in the seventh experiment, you can see when the velocity of car in z direction is 70 meter per second, in that case, drag force is 88.68 Newton and lift force is 16.73 Newton. Next analysis will be about goal optimization. So from this design of experience and optimization, we got a set of different parameters. And from this set of different parameters, you can see that when the velocity of the car increases, the parameters like drag force and lift force also increases. Suppose you want to have a lift force to be 10 Newton maximum, right? So to have a lift force to be maximum 10 Newton, we can see that the velocity of the car should be in between 50 to 60 meter per second. You can see here, when the velocity of the car is 50 meter per second, in that case, lift force is 8.31 Newton. And when velocity is 60 meter per second, in that case, lift force is 12.01 Newton. So to keep a lift force to be in the range of 10 Newton, the velocity of the car will be in between 50 to 60 meter per second, right? In the next analysis, we'll try to optimize this one, that at what velocity the lift force should be 10 Newton, right? Let us set up that one. We have already done that goal optimization, right? Let us see that from here. And here in this case, we have already told that our target value is to get the lift force to be 10 Newton. To have that one, we need to specify the velocity of that vehicle to be in between 50 to 60 meter per second. And based on that, we have selected these different parameters. Let us see the scenario or goal what we have determined. While performing this goal optimization, it has undergone 4 design points. What it has done is, initially it has started simulation with a velocity of 50 meter per second. Next one, it has started the simulation with a maximum speed of 60 meter per second. In this way, it has tried to minimum the gap in between, and finally, it has obtained the optimum targeted value of our lift force as 10 meter per second. At 50 meter per second, we got lift force as 8.3 Newton and our targeted value was 10 Newton. In that case, we got a discrepancy of 1.688 Newton. In the second one, when the maximum velocity is 60 meter per second, in that case, lift force is 12.01 Newton. And in this case, we got a discrepancy of 2.01 Newton. In the third design point, it has tried to minimize the gap and it has kept a velocity of 54.55 meter per second. And based on this velocity, you can see that lift force is 9.83 Newton. And in this case, we got a discrepancy of 0.16. In our analysis, we have kept a discrepancy value of 0.1. So in design point 4, we can see that when the velocity of the car is 54.96 meter per second, in that case, we could achieve our targeted value of lift force as 10.08 Newton and we could achieve the target, right? This way we can optimize our goals based on our requirement, right? So to have a maximum lift force as 10 Newton, we need to run that vehicle with a maximum speed of 54.96 meter per second, right? Instead of stopping it here, we can go for some other parameters also. In the same way, you can optimize different parameters like coefficient of drag, even drag force also you can optimize. Here in this analysis, we have selected the velocity of the car as the input variable. Excluding that one, we can do some other things like we can change some design parameters, like we can change the dimensions of the car also to optimize the drag force. Okay. With this one, we'll conclude our today's analysis. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.